Great. So welcome to checkpoint 3 by group 12. And in group 12, there's Sung Young Chang, Caleb Day, Avery Fry, Brittany Gear, and Philip Goldberg. In this checkpoint 3, we're going to run several tests, checking out several assumptions on the MLR model without any interactive terms, that is, or any exponential terms. Uh, so our test we're gonna be looking at is like linearity, constant variance, whether or not that exists, whether or not errors or like the errors usually like follow like a normal distribution. And we're also going to look at outliers plus influential terms. We're also going to look at the, interactive terms or interactive effect between the continuous variable with the poverty tier and other stuff as well. So on to our first test, which is linearity, which is on the next slide over. Uh, we see the residual versus the fitted plot. So in this case, we're comparing the y variable with the, other x variables. So this is the MLR without any of the interactive or like exponential terms. So it's just simply just like y and then x1, x2, x3, etc. Uh, and as you can see in this left plot right here, which is like the residual fitted plot, we could see that here, there isn't exactly a linear relationship between uh, the group of x variables and the y variable in this case. We see there's a slight curvature in this plot. And then if you were to go to the partial regression plot, which is essentially we're testing whether or not there is a linear relationship between the y or response variable and each of the individual x or predictive variables, putting the other variables constant. And in this case, we could see like, hey, for like each of the like x or predictive variables, we see that there is some sort of linear relationship between the like each individual x variables and the y variable in this case. So from this in conclusion, we can say that, hey, there is not a linear relationship between the x variables and the y variables in the MLR. However, we do know that there is some sort of linear relationship between the y variable and each individual x variable in this case, which basically means that there is some sort of interactive term within the regression, or should be included in, rather, in the regression. And then we will go to Philip, and he will tell you about the constant variance test in that case.
Moving on to constant variance, the residual plots can also be used here. What we're looking for constant variance for the residual plots is that there's no noticeable data pattern for all of the data points across zero. We can use the residual versus fitted x predictor plot, as well as the residuals versus the fitted y hat plot to determine if there is a constant variance. Looking at the plots, there is not really a noticeable data pattern for the points across zero, and they appear randomly scattered. This random scattering suggests that there is a constant variance in the data. But moving on to specific statistical tests, we can use the Brush-Pagan test as well as the Brown-Forsythe test. The Brush-Pagan test is mostly used to test the statistical model for constant variance. And for this confidence interval, we're working for a p-value of less than 0.05. And in this test, there is a p-value of less than 0.05 with a p-value of 0.0001258. What this means is that the test rejects the null hypothesis that the variances are equal, and the model does not statistically exhibit a constant variance. On the other hand, for the Brown-Forsythe test, which is also used to test for constant variance, this p-value is above 0.05. There's a p-value of 0.09347. This test actually doesn't reject the null hypothesis that the variances are equal, and is suggesting that the model between x and y does not have a statistically significant proof to suggest a non-constant variance. What could cause this difference is that the Brush-Pagan test is known to be more sensitive to outliers as it is mean-based. while the Brown-Forsythe test is a median-based test. So this difference in results can suggest the presence of outliers, but that consideration will be discussed later.
So now we're going to look at our normality of errors assumption. We're going to look at the histogram, the QQ plot of our residuals, the histograms also of our residuals, and then the results of the Shapiro-Wilk test. So looking first at the histogram of our residuals, we see it generally follows a normal curve. We see it might be slightly heavier tailed on the right. And then it also seems like a greater density of our residuals is at that just slightly less than zero than that above zero. So that's slightly concerning, but the general shape is normal. Looking over to our QQ plot though, that's where things start to fall apart. We see at a theoretical quantity greater than one, we start to drift away from that red line, indicating again that we might have some issues with the normality of our errors. And then the Shapiro-Wilk test kind of removes all doubt. Granted, that is impacted by sample size, so we have to take this result with a grain of salt and compare it to what we see visually. But again, it confirms that we do have an issue with normality of errors, so we will want to consider that and potentially transform our response variable y when it comes time to create our final model.
So in our analysis, we checked for unusual or influential data points in our regression model using 3 diagnostics: studentized residuals, leverage, and Koch's distance. So first we looked at the studentized residuals, which measure how far each observation's actual value is from the model's predicted value relative to its standard error. And then we examined leverage, which tells us how unusual an observation's X values are compared to the rest of the data. Finally, we used Koch's distance to measure how much the overall regression model would change if that observation was removed. Okay, so first we carried out these analysis on the individual SLR models of the 4 variables, where we have the Koch's distance and leverage and our student values plotted out over here. So the calculated cutoff threshold for leverage was 0.015, and the calculated Koch's distance threshold was 0.015 as well. And we were able to see which rows or which data points inside the CSV file was indicating the high Koch's distance value, as well as the data sets that are beyond the leverage threshold of 0.015 and beyond the studentized residual values of 3. Then we've ordered them in the top 5 influential observations, which is arranging the outliers based on the Koch's distance, the 5 maximum data sets that have the largest Koch's d values were indicated as these 5 rows. And we've also did the same thing for the unemployment percentage, where we saw over 10 data sets with high leverage and 17 data sets beyond the Koch's distance. The next variable studied was the poverty percentage, which also showed 12 data sets beyond the leverage threshold and 17 data sets beyond Koch's threshold. And for the police control data set, we've seen 18 data sets beyond the leverage threshold and 13 beyond Koch's distance. In all of the 4 variables, we've noticed that row 224 appeared in all of these outlier analysis, and so we can determine that row 224 is definitely an outlier in the SLR models for all of the data. And then finally, we did the outlier analysis also on the MLR model. The calculated Koch's distance threshold was also 0.015. The R studentized value was 3, and the leverage threshold actually increased to 0.038 after it incorporated all the 4 variables. And then we looked into the top 5 data sets that have the highest Cook's distance values. And here we also observed that row 224 exists.
Hello, I'm Brittany, and my section for the checkpoint 3 was on the poverty tiers and the interactions of these poverty tiers on the continuous variables. So I started off with calculating the different poverty tiers. We used the percent population under poverty column to calculate them, and we just divided them evenly into 3 groups. So the first tier I named low, the middle I named mid, and the high tier I named high. So this is the MLR showing the interactions between the poverty tiers. I used this formula up here, which is just all of the continuous variables multiplied by the poverty tier. These intercepts right here are all based off the low poverty tier. It used the low as a default. So these are the default values. And then these down here are all of the mid and high values for the poverty tier. So as we can see, based on these p-values, they're all pretty high. They're all above the alpha level of 0.1. So this shows that the effect of the poverty tiers is insignificant on the effect of the continuous variables on the y variable. I also ran an ANOVA test based on the original model versus the tiered model. So we have the original model here, which is just all 4 variables added to each other, versus the tiered model, which is just the 4 variables multiplied by the poverty tier. And this p-value was also insignificant at 0.18. So we can conclude that the impact of the continuous variables on y is not different based on the poverty tier.
In conclusion, we will need to transform our response variable y to try and negate some of the issues with constant variance and the normality of errors. We will need to remove a couple outliers to clean up our data. And we have determined that we will not incorporate the poverty tiers just because they didn't contribute to our ability to predict the response variable y. Thank you.